Welcome to the ABCs of peptide sequencing by MSMS. This is the first of 3 mini screencasts that'll help you understand the mechanism of the way peptides break in the gas phase. Think about how you feel when you see this. This is a peptide MSMS spectrum. You put in the mass spectrometer, run it into some neutral ions. I'm sorry, there's no such thing as a neutral ion. Run it into some neutral gas like argon or nitrogen, and it breaks and it makes this stuff. So how do you feel? Do you feel angst? Are you scared? Are you feeling a sense of resignation? If I show you this at the end of this lecture, the set of lectures, you're going to feel much better about it. We have to memorize this. There's no way around it. This is a peptide. As you'll see in a few slides, the peptide is going to break wherever a proton ends up, and the peptide generally will break here at this bond, the amide bond. This is an amide bond. It's carbonyl, nitrogen. In between it is the amide, and if it does, it makes a B ion. Now, B ions are the parts that contain the N terminus. If it breaks here, it also makes a Y ion, and the Y ion contains the C terminus. The labeling convention is that this is the first B ion. It contains the first amino acid. The second B ion, the third B ion. The opposite for Y ions. So in other words, what is B1 is the smallest B is the largest Y. The first amino acid on the C terminus is here, so it's Y1, Y2, Y3. So B and Y are corresponding corresponding ions, but you can also break here. And if you do, you make an A ion. And of course you can break here and make a C or a Z or a Y, but they're much less likely in collisionally activated dissociation. We'll talk more about them in the future. So let's start by looking at how peptides are made. This helps because if you can understand how a peptide bond is formed, you understand how proteins are made. You start with this entity, just an amino acid in solution. It's a Zwitter ion, negative charge here, positive ion charge here. The reason it's negatively charged, this is a carboxylic acid. They have a pKa of around 5, and it's in neutral pH, and so that means an acid will be deprotonated at a pH above its own pKa. So it's deprotonated. This, on the other hand, has a pKa of around 12. It's a strong base, the amino terminus, maybe 11. It'll pull a proton right from solution, right off of water. Zoink! Okay? So these two will bond, and water will be lost, and you'll make a dipeptide. Now, when we talk about residue masses, and we're going to be doing it for the rest of the class, so pay attention, we're talking about this entity right here outlined in red. How the residue masses differ from the termini is important. You can see this termini has an extra hydrogen and an extra proton. The proton turns out to be not as consequential because you're going to subtract it away during your deconvolution step. And if that doesn't make sense now, it will. There's also an extra oxygen here. Now, in mass spec, this is in water. In mass spec, we're going to spread out, neutral water. In mass spec, we're going to add formic acid, and so we're going to be spraying out of an acid. And in that case, this will be, the terminal will be OH. Okay. Important thing is just remember there's an extra water on every peptide that isn't in the residue masses, and we need to account for that. This is an amino acid residue. The R, if it's hydrogen, we have glycine. The amino acid residue doesn't have this extra water, and now I'm showing it with the electrons. So that instead of these straight lines, this is a one electron, another electron, that's a covalent bond, double bond, lone pairs on the oxygen, lone pair on the nitrogen, half of a bond because this is probably bound to something else that I'm not showing you yet, and then our R group. Throw in another one of these, dipeptide, tripeptide. Remember, those are the residues. What do we have to do on the N terminus? You have to add a hydrogen. Also, if it's in water, it's going to see a proton. It's going to zoik it over. And now we've assembled what is on the N terminus. Perfect. I'm not showing you the C terminus yet. We don't need to. For now, let's just say this is hanging off. Something's on there. It doesn't matter for this discussion. Now, we put this in the gas phase, we bump it up, get it vibrationally excited, and this proton becomes mobile, and it's called the mobile proton, and it's going to find a lone pair, or technically a lone pair will find it. Hey, lone pair, I'm a mobile proton. Whoa, hey, I see another lone pair, zoink. Hey, another lone pair, zoink. And so it goes. The proton can move back and forth from one place to the other during heating, but if it stops, wherever it stops, there's going to be a bond broken. Okay, that proton is what's controlling this bond breaking. And here we go. This is the essence of CID. Now pay attention. Look at this positive charge that was from the proton that had been bouncing around, and this electron. They're going to switch places. Whoa. And let's keep going back and forth just to make sure you see that. You got an electron and a positive charge switching places. Now what happens when an electron goes from a bond to a lone pair? Bond to a lone pair. That's what happens. It breaks. There's no more bond. And what we've created, assuming that we started with a singly charged peptide, is a B ion and a neutral peptide. Now this neutral is exactly like any other peptide, but we don't see it in the mass spectrometer. Now in our next lecture, we'll get into this, which is another way of rendering a B ion, and how we make other ion types.